I know you guys have always really wanted to know, is it true that an iceberg is really 90% underwater and only 10% above water? Well, to be honest, you've already been given the tools to solve this question, and I'm going to prove it to you. So imagine we have the surface of some water, okay? And imagine you have an iceberg floating in that water. So it's like, yeah, this is what you see from the surface. This is how much is actually underneath. All right. To begin answering this question, let's always draw a free body diagram. It never hurts, right? So in this case, what forces are going down? Well, obviously, this iceberg has a weight. So we'll say the weight of the iceberg. Okay. And there must be some force pushing up. Otherwise, this iceberg would just float to the bottom of the ocean. As you guys know from the last video, that force going up must be the buoyant force. So up is buoyant force. Okay. All right. So according to our force calculations, that must mean that B must equal, the buoyant force must equal the weight of the iceberg, right? If this thing is actually, floating, if it's not sinking and it's not rising up into the sky, these forces must be equal to each other, must be balanced forces, right? But we also know from Archimedes' principle that the buoyant force is equal to the volume of the water that's displaced by this iceberg, right? So this iceberg, by resting there, has to push away this much water, right? It's pushing that much water away. And so that force is just going to be the density of water, right, times the volume that's under, right, that's under the water. So VU will be the volume that's under, times gravity, right? And the weight of the iceberg, right, is actually going to be the density of ice, right, times the volume of the whole iceberg. So that's going to be VI, right, equals G. Now, sorry, not equals G, but times G. Silly me. Okay, so what are we really looking for? So we want the ratio of the iceberg that's actually underwater, right? So in other words, we want VU to VI. This value is going to give the percentage. So this is the total volume of the whole iceberg, and this is the part that's just underwater. So this should give us the percentage of the iceberg that's underwater. Okay? So let's see if how that works out. So first of all, it's so satisfying. We see these two G's. We can automatically cancel them out, right? And if we want to solve for VU over VI, then I would just divide by VI over here and divide by this density of water over here. So it's rho I over rho water, right? So it turns out the density of ice is a little bit less than the density of water. Okay, you guys may know that. That's why ice cubes do float, right? And according to my research, the density of ice is about 920 kilograms per meters cubed. Okay, and the density of water, specifically salt water, because this is out in the ocean, right? So technically, I'm going to put an S there for salt water. The density of salt water is about 1,020 kilograms per meters cubed, a little bit more dense than actual water, okay? And it turns out that if I divide these guys by each other, I get approximately 0.9, which, friends, is 90%. So we have just proved, using simple analysis of buoyancy, of Archimedes' principle, right, that 90% of the iceberg is a fraction that's actually underwater. And so when everybody says you only see 10% of the iceberg, 10% is the tip of the iceberg, that is actually pretty damn accurate. So wow all your friends with this simple mathematical calculation. In the next video, we're going to talk about an equally interesting example, a blimp. Specifically, we're going to look at the Hindenburg.